So in this lecture, we're going to look at some properties of the molecule benzene. So benzene is a really important molecule in organic chemistry and has some really interesting properties. And these stem from the fact that benzene, which is this molecule, is more stable than expected. In fact, this stability can be classified by a particular term called aromaticity. So aromaticity is kind of a description of molecules, or a classification mostly. Whatever, those are pretty similar. But you say a molecule has aromaticity. So if it follows a set of rules. We'll go over those in a second, but another term we could say is that benzene is aromatic. Now, aromatic has this kind of tone as though we're talking about the odor of something having some aroma. That may have been the case when aromaticity was first discovered, as we kind of saw these molecules kind of persist because they're particularly stable. They don't undergo the typical types of reactions that we would see in unsaturated or carbon-carbon double bond forming or containing molecules. So these things are more stable than expected, and some of them may have smells. And so we attributed them, or we said that they were aromatic. That's not necessarily the case now. Aromaticity is a classification of molecules that are more stable than expected and don't undergo the same types of reactions that molecules without aromaticity would undergo. So let's get right into it. What are the rules for being aromatic? The rules for being aromatic are that 1, you have to be cyclic. That is, the molecule must have a ring. Okay, that's rule number 1. Now, within the ring, I don't care what's happening outside the ring, within the ring, the molecule must be flat. We can have three-dimensionality and non-flatness everywhere else, but within the ring, we must be flat, which is to say that we're planar or sp2, planar. Planar is kind of the key word. There are ways to squeeze an sp hybridized atom into these things and still maintain aromaticity, but mostly we're sp2. Now, also within the ring, we must be conjugated. We must be conjugated, and that's alternating double, single, double. Or lone pairs. That are delocalized. And delocalized just means in resonance with. They're not fixed in a position. They can move through resonance structures, delocalized, or in resonance with the other pi bonds. And again, we're focused on within the ring. We could have a whole bunch of stuff out here, but I'm looking at a ring inside of our molecule, that ring being flat, and that ring having a conjugated pi system. And by conjugated, the ring must be fully conjugated. So we can't have some of the atoms within the ring conjugated and some not conjugated. They all must be conjugated. Now, in addition to that, rule number 4, within the ring, the ring pi electrons must satisfy Huckles Rule. Okay, so that's a new one. The other things, you've at least seen before. We've talked about conjugation, and then in organic 1, we looked at planarity and when that exists. And we've also, seen rings everywhere. But number 4, Huckles Rule is a bit new. So Huckles' rule relies on an equation. It says that Huckles' rule says that the number of electrons in a cyclic conjugated and planar pi system must satisfy the 4n plus 2 rule to be aromatic. So for the ring that's planar and conjugated, to be aromatic, we must satisfy the 4n plus 2 rule or the 4n plus 2 equation. The 4n plus 2 rule / equation is 4n plus 2 must equal the number of pi electrons in the flat conjugated ring. Okay, so we're just looking at the pi electrons, not sigma electrons, the pi electrons, and only those within a ring. They must follow the 4n plus 2 rule, where n is equal to 0 or a non-negative whole number. That is to say, if we could find a way to make this, let's cross it out in red, -1, 0, 0.5, 1, 2, 2.5, 7 halves, and 16. Okay, Huckles' rule is only followed if we have a positive whole number resulting from this equation. Okay, so that is the number of pi electrons is equal to 4n plus 2. What we do is we solve for n, and if n is any of these, for example, numbers, we could also have 3, 4, whatever, a whole number that's positive and includes 0, we satisfy the 4n plus 2 rule and we stand a chance of being aromatic. Okay, so we have the 4 rules: cyclic, planar, conjugated, Huckles' rule. Huckles' rule is the most complicated of them in terms of what you're familiar with. So let's go ahead and go right into an example of this with benzene. We started by saying that benzene was aromatic. Can we show that with these rules? Well, let's first of all recognize that indeed there's a ring present. Now within the ring, we have a planar structure, and within the ring as a planar structure, we have conjugation. Now, within this planar conjugated ring, we could ask ourselves 4n plus 2, i.e. Huckles' rule, is that satisfied? Well, 4n plus 2 has to equal the pi electrons. The pi electrons are 6 because we have 3 times 2 electrons per double bond. And we have 3 double bonds. So 3 times 2 is equal to 6. So we have 6 electrons total. So 4n plus 2 equals 6. Now we solve for n and we say that Huckles' equation is satisfied if n is a whole positive number. Well, if we subtract 2 from both sides, we get 4n is equal to 4. Divide by 4, we get n is equal to 1. And we say that Huckles' rule, or the 4n plus 2 rule, is satisfied. Terrific. We've done all 4. Cyclic, conjugated, flat, Huckles' rule. We are aromatic. Terrific. Benzene is aromatic. We knew that, but we at least used the rules to get there. Now let's look at some other interesting molecules. What about Cyclo, Octa, Tetraene? So Octa gets us a stop sign because we're Cyclo, Octa, Tetraene, and we're going to do 1, 3, 5, 7. So if we start 1, 2, 3, 5, and 7. Okay, so I picked the one that stands a remote chance of being conjugated. So I asked the question 1, is it cyclic? Check. Within the ring, and there's only a ring, is it flat? I don't know, seemingly, like Willoughby's probably not going to try to trick me on this aspect of it because we're trying to do organic chemistry in a two-dimensional surface. So flat, probably. Let's keep going. Okay, conjugated. Sure. Double, single, double, single, double, single. Check. Sure. Okay, Huckles rule. This is what we really want to get to. So in Huckles rule, what we want to do is we want to set the number of pi electrons equal to 4n plus 2 and solve for 2. Here we have the number of pi electrons equaling to 8 electrons because we have 4 double bonds and each double bond supplies 2 electrons to the conjugated pi system. So it's equal to 4n plus 2. Sorry, I forgot my plus up here. Subtract 2 from each side. We get 6 equals 4n. Divide both sides by 4. And I get an n is equal to 3/2. Wah, wah. If n's equal to 3/2, we don't satisfy the octet rule and we're not aromatic. The octet rule. What class is this? Huckles rule. Huckles rule is not satisfied. Huckles rule is not satisfied. We're not aromatic. Job's done, right? Actually, we've got a rule of not aromaticity, but anti-aromaticity that we need to consider. Okay. So the next rule to consider is the, if we're not aromatic, we should consider the 4n rule of anti-aromaticity. So the 4n rule of anti-aromaticity says that if the number of pi electrons it satisfies equals 4n, where n equals a positive integer, if this is the case, and we can get some number like 1 or 2 or 3 or 4, and we are all the other things, cyclic, planar, and conjugated, then the molecule is anti-aromatic. So the 4n rule sort of works like the 4n plus 2 rule, but the outcome is the exact opposite. We get to something that's anti-aromatic. And being anti-aromatic says that the molecule is less stable than would be expected, or is more unstable. Molecules that are anti-aromatic don't often exist. Oops, did I say that? I was defining anti-aromatic as though it was some real thing that people encounter all the time. Instead, I just wrote don't often exist. Let me just leave that in parentheses and write molecules that are anti-aromatic are highly unstable. Don't often exist. We'll have to get back to that in a second, but let's go back to Cyclo, Octa, Tetraene. Cyclooctatetraene. Oh, God. Okay. So cyclooctatetraene has 8 pi electrons. And so if we set 8 electrons is equal to 4n, then n is equal to 2. N is equal to 2. So cyclooctatetraene is not aromatic, it's anti-aromatic. Right? No, but we're going to write it down anyway. Okay, so cyclooctatetraene is anti-aromatic. Well, really, it's then cyclooctatetraene is anti-aromatic. The answer is not so fast. It turns out that what we're doing with cyclooctatetraene is the molecule itself, it's not us, the molecule itself is recognizing that it's pretty close to anti-aromaticity. And so what it's going to do is find a way to avoid anti-aromaticity at all costs. What does that mean? How can you avoid being anti-aromatic? Well, let's think about what it takes to be anti-aromatic. It takes all the things it takes to be aromatic, but you're going to follow the 4n rule instead of the 4n plus 2 rule. So you're going to be cyclic, you're going to be planar, you're going to be conjugated, and you're going to follow the 4n rule to be anti-aromatic or more stable than expected. Okay, so if a molecule wanted desperately to not be anti-aromatic, what could it do? Well, one approach is that it could find a way to not be cyclic, planar, conjugated, or follow the 4n rule. Well, we probably won't break a ring in most cases. So we're going to be cyclic no matter what. We could avoid the 4n rule, right? If we took on more electrons, well, that's a chemical reaction. Let's assume our electrons are stuck at 8. And we're always following the 4n rule. So then the answer is to break away from either being planar or conjugated. It turns out those two things are the exact same thing. Okay, so anti-aromatic molecules I was thinking about something that I wanted to say. Anti-aromatic molecules, and put that in quotes. That's what I was thinking about. Anti-aromatic molecules will avoid being aromatic by distorting themselves away from aromaticity or from planarity. Planar or conjugated, to be specific. So they're going to find a way to avoid being either planar or conjugated. Well, how does that work? Well, it turns out that the actual geometry of cyclooctatetraene isn't what you would expect. It's not this beautiful flat octagon where all the bond lengths are identical and that sort of thing. That's not realistic. Instead, the molecule, recognizing that it could become anti-aromatic if it's not careful, sort of adopts a chair structure. So it bends and distorts, excuse me, away from being planar. So it distorts away from being planar. And if it's not planar, it's not aromatic. Okay. So why is this the case? Why is planarity so important here? Okay, let's look at everything so far. The electron count may not be super intuitive, but conjugation kind of makes sense because conjugation is what's required for all of the electrons to exist within molecular orbitals within the ring system. Okay, now the ring is required because that allows for the electrons to easily go from start back to the beginning, like kind of circumnavigate in either direction quite effectively. So we can kind of more fully delocalize across the 6 atoms. More on that later. But what really comes to bear here in terms of the flat thing is the fact that being flat is closely related to being or being planar is closely related to being conjugated. So it turns out that being planar is required for being conjugated. Okay, now to understand that, we need to look at how conjugation works. So it turns out that conjugation occurs when p orbitals are parallel to each other. So what's required for conjugation is for p orbitals to be parallel to each other. So we have parallel p orbitals here. Now what I want to do is actually draw maybe another p orbital. So these first two may form a traditional pi bond, but this third one, being parallel, kind of wants in on the action, and maybe it provides electrons. So you put these all together, and you have all of these parallel bond p orbitals, and maybe they're even in phase, and you get to a nice pi 1 molecular orbital of butadiene. Now, it's important that the p orbitals be parallel to each other because that's how you delocalize the electrons. That's how resonance structures get involved. For one electron to jump from one side over to the other, which we do with curly arrows, we have to have orbitals for those electrons to enter into. And the best way to do that is to have whatever orbital that electron starts out in just be parallel so that it can kind of overlap with the orbital on the atom next door. Because if they're parallel, then they can form a molecular orbital because they're all in phase. If they're anti-parallel to each other or orthogonal, let's imagine one's pointing up and one's pointing down. There's no overlap here, and the electron can't jump from this orbital to this orbital. They have to be parallel so they can go from here to here with ease. Okay, so that's the pi 1 molecular orbital of butadiene. It turns out that a similar thing can be seen with benzene. So the benzene molecular orbitals for the pi system, let's just draw one. Let's just draw the lowest energy molecular orbital. Well, it turns out that if benzene looks like this, and it can have resonance where the, oh, I moved nuclei, that's not right, where the double bonds can exist in these two orientations, now there's many other resonance structures, but these are two of the degenerate highest contributing resonance structures. But for the electrons to freely move about any of the 6 atoms, they can kind of just keep swinging around so long as they're always alternating. For that to occur, we have to have parallel p orbitals at every atom. And what that looks like is a situation like this, where at each of the atoms within the hexagon, we've got, in this case, I'm going to put in phase shading region on the top every case, and you can see they're parallel throughout the entire thing. So maybe it's hard to tell with some of the lower ones, but just picture that's a flat benzene that's tipped forward. So there's a little bit of perspective in here, but all the p orbitals are parallel. So maybe I didn't do a good job of explaining that, but I had to tip that structure so you could see all of the p orbitals, and I've tipped it so that we can see them all. But in fact, all the p orbitals are parallel to each other. So all the p orbitals are parallel to each other in this depiction. And this would be pi 1 of the molecular orbital. So what happens is that the anti-aromatic structures can distort themselves so that p orbitals are no longer parallel to each other and resonance cannot occur. So p orbitals are not parallel to each other. So in the case of cyclooctatetraene, we saw that the structure now adopted itself in such a way that, yeah, maybe the p orbitals in that pi bond are parallel, but they're not parallel to the p orbitals in the other pi bonds. So this is pretty remarkable. The molecule, whatever the meaning is behind the 4n rule, which we're not going to get into right now, we can look at that later, especially when we're in front of WebMO on the computers. We're doing calculations, but in this depiction, all of these pi bonds, all 4 of them are isolated from each other. They're not in resonance. They're not conjugated because it's not flat. Because it's not flat, the p orbitals are not parallel. And if you're not parallel, you're not conjugated. And conjugation is the critical piece here. It's just to get everything parallel, we have to be flat. So maybe a better, descriptor would be all of the p orbitals are parallel, but it's a little bit easier to tell if a molecule is flat or not. Okay. So we can distort by bending the geometry so the p orbitals are not overlapped with each other. Now, what's the result here? Is it aromatic? Well, we know it's not aromatic because it doesn't follow the 4n plus 2 rule. But then, is it anti-aromatic? Anti-aromatic meaning highly unstable? I mean, the 4n rule is satisfied, but we're not flat. If we're not flat, we're not conjugated. If we're not conjugated, we can't be aromatic or anti-aromatic. So that's not the case. So then what are we then? We're not aromatic. We're as aromatic as methane, as CH4. We've just found a way to make it so that the conjugated pi system is not conjugated. If it's not conjugated, the pi system is 4 separate pi systems with 2 electrons. It's not aromatic. That's not even really a conjugated system within a ring, okay? So we say that the molecule is not conjugated. We can have other examples too. It turns out that if you take cyclobutadiene has 4 pi electrons. It appears to be flat. It appears to be conjugated, alternating double, single, double, single, double. And it's in a ring. So is it aromatic or anti-aromatic? Well, 4 that follows the 4n rule. And if it follows the 4n rule, right, because 4 equals 4n, divide both sides by 4, n equals 1. I'll get rid of that divide by 4. You could have done that. Okay, so we're at a positive whole number with the 4n rule, but not the 4n plus 2 rule. So we satisfy the anti-aromatic equation. So are we anti-aromatic? Well, the answer, as soon as we want to write yes, anti-aromatic, we have to stop ourselves and say, but how's the molecule going to get out of this bad situation? Because the answer isn't that it's anti-aromatic. The answer is that it's not aromatic. Well, and I've kind of alluded to it here, but what cyclobutadiene does is this molecule stretches to avoid true conjugation. And I've kind of drawn the structure fairly accurately, but there's double bonds that are separated greatly at great distances from each other. And because these single bonds have stretched so much, we're not truly conjugated anymore. The p orbitals in these neighboring pi systems that need to be parallel to each other may be parallel, but they're so far away. And that means we cannot be in conjugation. The bonds are just too long. Those single bonds are too long, and we cannot kind of even draw resonance structures effectively. I mean, yeah, I can push the arrows and do this thing on paper. Like I could take this and I could have some arrows to show the interconversion just like I do with benzene. But here's the thing about benzene, all the bond lengths are the same. So it doesn't care if you write a 2 or a 1, it's always 1.5. Here, you can't get to this resonance structure unless you do a chemical reaction or enter some sort of excited vibrational state. And as a result, we're not truly conjugated. So this is just another example of how a molecule will find a way to distort itself to avoid anti-aromaticity. So the answer is the molecule aromatic or anti-aromatic? The answer is it's probably either aromatic or not aromatic. If it can find a way to be aromatic, it's going to get there. But if it can't, then, you know, it'd just rather be anti-aromatic. So why do we need to even study anti-aromaticity if these things never exist? Why don't you just stop at the 4n plus 2 rule? Why are you going to make me learn the 4n rule? Well, anti-aromaticity is helpful to know about. In particular, the rules help us identify when molecules are unlikely to form. So when molecules are unlikely to form. And we could look at some chemistry of this, but I wanted us to just be able to identify aromaticity and anti-aromaticity in this kind of initial lecture. So I'm just going to go through a few more examples where we look at lone pairs. So aromaticity with lone pairs and charges. So it turns out that lone pairs can count in the 4n plus 2 rule if they get us to 4n plus 2. Okay, here's an example. Excuse me. Frog in my throat. Okay, so we have a 5-membered ring. I don't care about the methyl group hanging out. I just focus on the ring. So I've got my ring. And I guess I highlighted that. So I've got my ring. It is flat, sure. Willoughby's going to tell me if it's not flat, or I'm going to have to recognize it's anti-aromatic and make it so that it's not flat or something like that. So it's a ring, it's flat, and is it conjugated? Well, if it's conjugated, I can draw resonance structures to every atom within the ring system, and that includes the lone pair of electrons. So if we go and we take these lone pair of electrons, I could push them over here. Now, if I do that, and I've got a methyl group on the nitrogen, now I have a positive on the nitrogen, negative on the carbon. I could push these electrons here. Okay, so I have charge separation. I don't have as good of resonance structures, gosh, as I did originally. I can push the electrons over here. These are some fun resonance structures to draw, kind of challenging. But I'm just pushing the electrons around, and because the electrons aren't on the nitrogen's always got a positive charge, we're overall neutral throughout the entire scheme. Lone pairs now in southwest in this resonance depiction. I just use 2 arrows every time. Now if I go here, I'm going to push the electrons back and up and onto the nitrogen. That's going to give me back this original structure. Okay, so here the lone pairs can be, what we say is they can be moved or delocalized to all atoms within the ring system. So they can be part of the conjugated system. The conjugated pi system that when we started looked like it was just the 2 double bonds that were alternating with a single bond between them, but now also includes the pi electron, or excuse me, the 2 electrons that are lone pair on the nitrogen. So the number of pi electrons is equal to, it's not 4 from the double bonds, rather it's 6 electrons. And so if we have 6 electrons, that's the same count as benzene, where we can subtract 2 by both sides, divide by 4, n is equal to 1. And what that tells us is that if n is equal to 1, this molecule is aromatic. It's flat. It's cyclic. It follows Huckles' rule. It follows Huckles' rule because we could take that lone pair and spin them to every atom. Took 6 resonance structures to get there, but we could. And the nice thing is you only have to do that once. 5-membered ring with a lone pair. We can just do that once to think about for other molecules. So the nitrogen really didn't have anything to do with it, except it just provided a lone pair of electrons in a neutral state. I could take a more sophisticated molecule, which is cyclopentadiene anion, where instead of being neutral, it's now negatively charged, and do the exact same thing. And I could just keep doing this and roll those electrons throughout the entire ring system. But suffice it to say, they can go everywhere. It's just a 5-membered ring with 2 double bonds and a lone pair of electrons. We can spin the lone pair everywhere. The lone pair is in conjugation. And if it's in conjugation, what we can do is count it when we look at aromaticity. So is it aromatic? And the answer is, well, is it a ring? Yes. Is it planar? Probably. Is it conjugated? Yeah, it's as conjugated as that nitrogen molecule from before. And what about 4n plus 2? Well, it's got, again, 6 electrons, 6 pi electrons, 2 from the lone pair, 2 from each of the double bonds. Six pi electrons, that follows the 4n plus 2 rule. We've done that a few times now. So yes, it's aromatic. Okay. All right, last example, and we'll call it a night. And that is, what if we have 2, and I should box that. That's the big takeaway. What if we have 2 lone pairs on an atom within a 5-membered ring and 2 double bonds at the other atoms? Well, we could just use 1. Well, why is that? Why do we just get to use 1 and ignore the other one? Well, just like the molecule, I'll keep it simple. There's a really nice explanation of this where you actually look at the true nature of lone pairs on oxygen atoms, but it turns out it may have been a bit misleading in org 1. Let's not worry about that now. It turns out that just like before, when we were looking at anti-aromaticity, if a molecule recognizes that it can be anti-aromatic, it found a way to distort itself to get out of anti-aromaticity and not being conjugation. We can do the same thing with aromaticity, where it can distort itself to make sure that it can take advantage of an opportunity to be aromatic. So the molecule is going to use 1 lone pair. That gets us to something that's cyclic, that's planar. Yeah, I said ring. Okay, that's conjugated, because we'll just use 1 lone pair and ignore the other lone pair. So we use 1 lone pair, ignore the other lone pair. That gets us to 6 pi electrons, and we're aromatic. I realized I should just show one tiny example. Sorry. What if we have a lone pair that what this kind of illustrates is if we don't need a lone pair, we can just lose it when we're looking at aromaticity. So what about a molecule like this? Turns out this molecule is named Pyridine, and it smells putrid. It's fun. Okay, so this molecule is aromatic because what you can do is ignore the nitrogen lone pair and it's benzene, right? So if we could ignore the lone pair before, look at this. If you ignore that nitrogen lone pair and say, I don't need it because I've otherwise got benzene. So, and there's deeper orbital discussions about this, but I wanted to get us warmed up with identifying aromaticity in this module so that we could get hit the ground running in the next unit. So anyway, that'll do it for this lecture, and went a little bit long, but important stuff. Okay, so we'll see you next time where we continue our discussion of aromaticity and aromatic molecules.